Okay, so first announcement for today, I want to point out, I want to say this before I forget to. Um, so the original plan for the course was to use ProctorU, the proctoring system for our exams. I mentioned earlier in the course, I think that we were having some tech issues that we were trying to work out. Well, unfortunately, we haven't been able to figure out a way to work out those tech issues in a way that we're confident that when students would sign on to take an exam, that it would go the way we expect it to. We don't really have a good tech solution, and we don't really have a way to test or confirm the basically hack or workaround that we think we might have. So long story short, we're not going to use ProctorU this semester. Everything else about the exams will be the same. They'll be taken on WebAssign. The dates will be the same. They'll be in the same 1 week windows. All of those policies and details and dates and all of that are in the syllabus and course schedule on Blackboard. So check that out if you have any um, questions about those dates or policies or anything. Um, oh, is anybody else unable to hear me? I think somebody in chat says they're having audio issues. I'm guessing that means they can't hear me. Okay, let me just respond to him. Oh, somebody else says, okay. So it seems like audio might be cutting out for a couple of folks. Um, I feel like I'm in the can you hear me now commercial. I have actually done that before on Zoom. I thought that somebody else was muted and my sound was just turned off and I didn't realize it, but Zoom these days is a little smarter and it will like prompt you and say like your audio is too low or something sometimes. I don't know if it does it all the time, but all right, so hopefully everybody can hear now. If you're having trouble with audio cutting in and out, you might try. There's a way to turn on like captions or transcriptions for from your end. So if things are cutting in and out, maybe try that. That might be a good backup. Um, but I think it's working now, it seems like. Um, Yeah, so with ProctorU, I mean, everything else will be the same, the dates, the content of the exams, number of exams. The only difference is they won't be proctored at all because ProctorU is the only system we have access to, and it is obviously not really working. So at least not working to the extent that that me and a couple other faculty members would feel comfortable having students reliant on it for a high value exam. Um, so with that being said, no ProctorU this semester. We'll be kind of trusting that folks will follow the rules and will maintain the integrity of the course. But unfortunately, no ability to proctor this semester just because of the tech issues that we're experiencing. The plan today is to finish one last problem in trig substitutions and then talk about partial fractions, section 7.4. Also, my allergies are just going crazy today with the ups and downs of the temperatures the past couple weeks. Um, yeah, so that's the plan for today. And the quote of the day is from chess grandmaster Daniel Naroditsky. Uh, the idea of prosecute the advantage. So to prosecute most often is used in the legal sense, but it really just generally means to kind of move forward with a plan of attack. So take the advantage that you have and press forward with it to a conclusion. And I think the idea here is that there's kind of a difference between abstract versus concrete advantages. In chess, what that might look like if you're familiar with chess is, one of the challenges of chess is all of your good pieces are hidden behind all of your pawns, and it's a little bit hard to and kind of awkward to get your pieces out at the beginning of the game. So that's called the opening phase of the game. Maybe you have a couple extra pieces out over your opponent. Maybe you have three pieces out, your opponent only has one, because they had a little opening mishap or something. That's an advantage for you. You have a development advantage. But if you fall asleep at the switch, your opponent gets a couple more pieces out, that advantage has disappeared. That's kind of an abstract advantage. But if you take your piece superiority, 3 versus 1, and you can turn that into an attack, and you say when your opponent's light squared bishop, your opponent doesn't have a light squared bishop the rest of the game. You've prosecuted that advantage, turned it into a concrete advantage that now will last the rest of the game. And I think there's a lot of application in life of this idea, kind of playing your hand towards your advantages and away from your disadvantages while also working to shore up any weaknesses you have. But I think the most applicable to students is, most people who are taking college courses are looking to get a degree and then to turn that degree into a career. So something that either is financially rewarding or personally rewarding or purposeful, something along those lines, something you enjoy doing. But getting the degree, I mean, it's a great accomplishment, but it's an abstract advantage. That degree doesn't get you the lifestyle that you want, or the job that you want, or the career you want, or the purpose that you want. It kind of opens some doors, but you have to walk through the doors. So you have to take that degree, and maybe in the couple months before you graduate and the couple months after you graduate, press that advantage, prosecute that advantage, and turn it into job opportunities. Or maybe you shadow some folks to get your foot in the door somewhere, get people knowing your name, know who to contact or who to reach out to when you do apply. And those kind of things set the stage to be able to turn that degree into a career, into a lifestyle, into purposeful work, whatever it is that you're seeking from that degree. So I think that's one good example of this. Okay, so finishing up trig substitutions, we looked at this example briefly at the end of last class. And we said, okay, well, the idea of trig substitutions is I want to pick maybe x equals, maybe say something like sine theta. And the nice thing about that is that, for instance, 1 minus x squared, 1 minus sine squared theta is cos squared theta. And particularly if I have this like under a square root or something like that, that's pretty nice. So if I have a variable squared, a lot of times a trig substitution will be helpful because I can translate sine squareds into cos squareds. I can translate those back and forth. Now, if I look at this particular example, and again, implicitly, I would always kind of start back at basic, my basic, uh, derivative or integral rules. Do I just know that this is the derivative of something? You actually might know this one off the top of your head, but we're going to kind of pretend we don't. Is there a basic substitution I could do here? Not really. The only thing I could really think of is u equals 1 plus x squared, but then I don't have a nice 2x to mesh with that substitution. Is there anything algebraic? I can do an algebraic simplification, anything like that, integration by parts. I don't think any of that's really going to work so nicely here. So we are going to end up using a trig substitution. Now, if I use x equals sine squared theta, or anytime you're using x equals sine squared theta, or sorry, x equals sine theta, you could basically use cosine as well. But if I use that, I see I'm going to end up with, say, a 1 plus sine squared theta. That doesn't work so nice, right? We have sine squared plus cos squared equals 1. Or that would mean that, say, cos squared is 1 minus sine squared theta. So if I had a 1 minus x squared, that might work out nicely to use like x equals sine theta. But I have a 1 plus. Well, I have different versions of the Pythagorean identity. I can divide both sides by cos squared theta to get tan squared theta plus 1 equals, well, what's 1 over cos squared theta? I think that's secant squared theta. So actually I see that x equals tangent theta works maybe pretty nicely with 1 plus x squared type of situations. So the Pythagorean identity that lets me do 1 plus something squared and simplify that, I'm looking at the substitution x equals tan theta. And then 1 plus x squared, 1 plus tan squared theta is secant squared theta. So this whole denominator, 1 plus x squared, turns into secant squared theta. This seems pretty disappointing at first, because I say, oh man, now I have a 1 over secant squared theta, or maybe I flip that up and get an integral of cosine squared theta. Maybe I can deal with that, but that's going to be a bit of a pain. I mean, I can at least maybe see a way forward, but remember, the bookkeeping is super important here. It's really easy to do something like this and make an error. I have this dx. So what is dx then? Well, the derivative of tangent is actually secant squared. Dx is actually secant squared theta d theta. This actually turns out super nicely. Secant squared theta over secant squared theta is actually just 1. Or integral d theta is just theta plus c. Now, my original question was phrased in terms of the variable x. I have an answer in terms of theta, but theta was the variable that I kind of invented. I want to get this back into x. So of course I arctan both sides. So theta is inverse tangent of x, or arctan x, plus c. We might also have recognized this just from our differentiation properties. We might have remembered back when we were in Calc 1 differentiating the inverse trig functions, arcsine, arccos, and arctan, that we got something that looked like this for the derivative of arctan x. So if you recognize it right off the bat, that's perfectly fine. But I'm just doing this as an example of a slightly different trig substitution other than sine or cosine. When we see this 1 plus x squared popping up, we might want to look at x equals tan theta as a possibility. Now, again, sometimes maybe I see a 1 plus x squared and I say, oh, is this trig substitution going to work? And maybe sometimes it just ends up as such a mess that that wasn't the right way to go. And I back up and I try something else. Maybe I try partial fractions, for instance. But in this case, it worked pretty nicely, especially because our dx meshed very nicely with our integrand. So really big takeaways, especially in trig substitution, this bookkeeping is super important. This just being really careful that each step you take, each piece of the integral, whether it's kind of the integrand itself or the dx that we often just kind of want to treat pretty flippantly, that we really take care to evaluate each piece properly, and that we don't skip over anything that's in the integrand. So in this case, this dx contributed substantially to the integrand of the theta integral. Okay. And I suppose one last thought on 7.3, note that 7.3, when we're talking about trig substitutions, these are actual substitutions. We went from an integral in x to an integral in theta. This is contrasted with integration by parts, which kind of had that u and v floating around, but it wasn't actually a substitution. So we just also want to be cognizant of, are we actually changing variables or not? If we are changing variables, that often suggests a need to change back at the end of the problem, or maybe if we had a definite integral here, our theta bounds would be different than our x bounds. We saw that in an example last time with the area of the ellipse. We had to adjust our bounds when we moved to the theta integral. Or in an indefinite integral, we need to take the step to get back to the original variable. That was what the original question was posed in. We should get back to that variable for the answer. But just keep in mind that 7.3 trig substitutions, and of course, just our standard U substitutions at the end of chapter 5. These are legitimate substitutions. We're changing the variable of integration from one step to the next, so we have to respect bounds or getting back to the original variable at the end. Integration by parts was just kind of basically a bookkeeping method. And from one step to the next, we didn't change variables of integration just by using integration by parts. Now, if we use integration by parts in conjunction with, say, U substitution, if we combine those techniques together, we might have to make adjustments. But just using integration by parts itself does not change the variable of integration. Okay. Any questions on 7.3, trig substitutions? So I think trig substitutions are one of those things that seems a little scary, but if you know the patterns, if you see a 1 plus x squared or a 1 minus x squared, think about a trig substitution and just be super careful with your dx. Those kind of two prompts, I think make trig substitutions not too bad. And then, of course, just kind of knowing your basic trig relationships, your Pythagorean identity, like how the right triangles come together, things like that. Okay, so what's the idea of partial fractions? Partial fractions is another integration technique. It's another integration technique like trig substitutions that sometimes people think is very difficult. I don't think it's that bad. I think the difficulty comes from the fact that there are a lot of steps in any given problem. But the nice thing about partial fractions is that, for some problems, we might have like 2 steps, but each step is really complicated or really a big pain or really difficult or confusing. Partial fractions, we're kind of exchanging maybe something like difficulty or complexity of calculus. Instead of doing like 1 or 2 really hard steps, we're kind of doing a whole bunch of easier steps, basically algebra steps. And that helps make the calculus a lot easier. That's kind of the trade-off here. These are long problems. They're kind of a slog. They're kind of a pain in the butt. But, it's a little bit like, walking a mile over flat terrain. Like, okay, it's going to take a while and it's kind of boring, but it's not that hard, right? Rather than like sprinting up a 45-degree hill, it's like, well, you'll be done quicker, but, you're going to be like on the ground gasping for breath at the end, right? So I think if you look at it that way, yeah, these partial fractions can be a little bit tedious and boring, but the reason they're tedious and boring is you're doing a bunch of algebra steps, and you just have to be careful with the algebra and arithmetic, and it makes the calculus a lot easier. Okay, so let's look at a motivating example. Let's take a look at just a numerical fraction 1/6. I'm drawing an analogy here, so this isn't going to be a perfect analogy. It's a little silly, like why would we do this? Why do we want to do this? But we'll see why we want to do this kind of thing, to help, say, solve an integral kind of like this one. But I'm drawing the analogy here with numbers so that we can see kind of the mechanisms that are going on before we jump into something with variables. I look at 1/6 and maybe for whatever reason, I don't like the denominator 6. It's kind of a complicated number, right? It's not a prime number. And I say, I know that I can make 1/6 by adding up fractions that look like 1/2 and 1/3. Is it 1/2 plus 1/3? Is it 3 times 1/2 plus -2 times 1/3 or something like that? Not really sure. But I kind of think that I could make 1/6 by combining together some number of 1/2 and some number of 1/3. Why do I think this is the case? Well, if I did like, let's just say 1/2 plus 1/3, obviously not correct, but if I wanted to add these, what's the first thing I would do? Get a common denominator. 2 times 3 is 6. And this would give me 3 plus 2. Well, this gives me 5, 6. So it didn't quite work out. But I see that maybe if I pick the right numerators, instead of 1/2 plus 1/3, maybe if it's like 3/2 minus 4/3 or something, or right, maybe I can pick the right numbers for the numerators so that when I add everything together, this 2 times 3 or 6 in the bottom ends up working out. And just erase all of this. Let me actually go back even further. There we go. So what I want to do is I want to pick a number a multiplied by, say, 1/2, or really this is just a over 2. So I have a certain number of 1/2, could be negative, could be 0, plus a certain number of 1/3, again, could be positive, negative, and I want that to be 1/6. I want to choose a and b to make this equation correct. Now, again, there's more degrees of freedom here than constraints, and so this isn't a perfect analogy with what we're going to do in a minute here, but I'm just illustrating the idea. Okay, so how should I choose a and b? Well, let me proceed forward. If I were to combine these two together, these two fractions, a over 2 plus b over 3, I would have 3a plus 2b over 6. Right, I multiply my first fraction by 3 over 3, get a denominator of 6, and my second by 2 over 2, get a denominator of 6. Combine them together. And I now see I have a constraint. These two have to be equal to one another. 1/6 has to be 3a plus 2b over 6, or that means 1 has to be 3a plus 2b. And maybe I choose to pick a equals 1 and b equals -1. So I say I desire to split 1/6 into a over 2 plus b over 3, because those are prime denominators. Maybe I just like dealing with smaller denominators that are prime numbers. If I do that, a over 2 plus b over 3 combines together to be 3a plus 2b over 6. And I have to have that being the same thing as 1/6. So 3a plus 2b has to be 1. And one way to get that, for instance, here is a equals 1 and b equals -1. So I can say that 1/6 is, well, that's 1/2 minus 1/3, for instance. And maybe now I can work with these 1/2 and 1/3 fractions that maybe are easier to deal with for whatever reason than the composite denominator of 1/6. This is the idea. We're going to be doing essentially the same thing, but with polynomials. We're going to be looking at rational expressions. Our denominators will be polynomials. And we'll say, I mean, it's kind of annoying to deal with such a rational expression as an integrand. But if I had like 1 over x plus 1, just a linear, I know this is basically like log x plus 1, right? If I have 1 over a linear under the integrand, it's just like log of that stuff. If I have 1 over a quadratic or a cubic or a quartic, that's a lot more complicated to deal with. So I can integrate 1 over a linear function really easily. I could maybe integrate, x over a quadratic, something like that, but substitution. So for these problems, I would want to check, does just a basic u substitution work? Does this integrate just to something like log of x squared minus 5x plus 6 or something like that? Maybe it does. In this case, we're not so lucky though. Right, if I did a u substitution, I would have 2x minus 5, nothing super nice on the numerator to work with there. But if I recognize that this denominator, x squared minus 5x plus 6, I recognize that it factors. It factors into x, let me come over here. It factors into x minus 3 times x minus 2, right? I have a composite number that factors into two prime numbers, or I have a composite polynomial that factors into two prime polynomials, x minus 3, x minus 2. Wouldn't it be nice if I could split this into, let's just say, for instance, 1 over x minus 3 plus 1 over x minus 2. Well, hey, I can do both of those integrals really easy, right? Now, I don't think that I'm going to get so lucky that it's going to be just 1 over x minus 3 plus 1 over x minus 2. Or even if I do get so lucky in this case, it's certainly not always going to work. But I might recognize that, well, okay, so I have a quadratic over here and a smaller degree polynomial in the numerator. So my x minus 3, I can't have any x's in the numerator. It can't be like x over x minus 3 is what I end up with, because then when I did polynomial long division here, I would get like 1 plus something. I would get something that's not a rational expression. That's not going to happen. This numerator is only going to be a constant, a over x minus 3. It can't be like ax plus b with a not being 0, because then I could divide out a constant part, and then I'd be saying that this quotient is actually constant plus, essentially a remainder. But that's not what it is. And I could say the same thing about the second bit here. It's going to be b over x minus 2. I can't have anything bigger, so to speak, than a constant in the numerator, because if I did, I'd be able to divide something out, get a constant term, and I don't see any constant terms on the left. So I'm going to find a and b that makes this statement true. Can probably get rid of these arrows. So that's my goal. I now have an algebraic equation. I want to find a and b that makes these true. So what do? I can multiply through by the product x minus 3, x minus 2. On the left, that just gives me 1. On the right, the x minus 3 factors divide from the first fraction, and I get a times x minus 2. And in the second fraction, the x minus 2 factors divide, and I get b times x minus 3. So now this is my equation. There's a couple ways I can go about solving this equation. One way that I could do it, and in more complicated problems, you might actually use a combination of these two methods. But one thing I could do is I could look on the right side, and I could say I have some x terms and some constant terms. So I have a plus b times x plus, and then for my constants, I have negative 2a minus 3b. On my left side, I have 0x plus 1. I have a 2 by 2 system. A plus b equals 0. The coefficients of x have to match. I mean, I could just imagine subtracting everything onto one side or something and, arguing that way. but I can pretty clearly see the coefficients of x have to match and the constant terms have to match. I have a 2x2 linear system. And I should know from previous algebra experience how to solve a 2x2 linear system, right? I see, for instance, that a is going to be negative b, so I have negative 2a plus 3a equals 1, and can go from there. That's one approach. Another approach is to substitute. So we'll use the substitution approach here. So this would be one approach, developing a linear system and solving the linear system. 2x2 linear systems aren't that bad to solve. If you get up to like a 4x4 linear system, it's a pretty big pain. But a second approach is to evaluate, just to plug in some values of x and see what a and b have to be. Now, there is a sense in which plugging in values of x and seeing what a have to be is basically just constructing a 2x2 system. But imagine if I had a 2x2 system that was like a plus 0b equals 3. I'm just throwing numbers out here. And 0a minus 2b equals 1. I mean, that's a 2x2 system, but it's trivial to solve, right? These 0 bits go away. I just see a is 3, b is negative a half. I can just essentially see that by looking at it. So, I mean, we're kind of still setting up a 2x2 system, but we're setting up a completely decoupled 2x2 system here. So let me look first at what gets rid of a. What value of x can I plug in that makes a just go away? Well, hey, if I plug in x equals 2, if this equation, 1 equals all of this stuff, has to work for all x, it certainly has to work when x equals 2, right? But when I plug in x equals 2, that zeroes out this first term on the right. I have 1 equals 0 plus, then I get b times 2 minus 3 is negative 1. Divide both sides by negative 1. Clearly, b has to be negative 1. If I make a go away completely, I just can solve for b trivially. How can I make b go away? Well, if I plug in x equals 3, that makes the b term go away. My left-hand side still is 1. The value of x doesn't change that constant on the left. The right-hand side, I get a times, well, here 3 minus 2 is positive 1. And then plus, but that's 0. 3 minus 3, 0 times b. That's 0. Or I see that a is just 1. So I found what a and b have to be, either through solving a 2x2 system or by being creative about my choices for x, plugging them in and solving that way. Doing this lets me decouple the information from a, the information about a, from the information about b. This 2x2 system is coupled. Each of the equations contains some information about both a and b. Where's the systems approach nice? Well, sometimes I have more letters, A, B, C, D, then I have really good candidates to plug in. That can happen in some cases. And then maybe I want to plug in the good candidates I have, whittle down the information a bit, and then maybe use a system to carry the problem to its conclusion. But either approach will get you the answer. But what do I see here? Let me just come down a little further so I don't run into my work over there. Note that what I've done here is simply an algebraic simplification. I'm simply rewriting my integrand as something that is algebraically equivalent. It's going to be 1 over x minus 3 minus 1 over x minus 2. all that I've done in this step is algebra. I haven't done substitutions, I haven't changed variables, I haven't done any of that. I've just done algebra here, just rewritten the integrand in a form that's a little easier for me to deal with. But my integral is linear, which means I can rewrite this as integral 1 over x minus 3 dx minus integral 1 over x minus 2 dx. And hey, each of those integrals, I just know how to do. I just recognize that this is going to be log absolute x minus 3, whoops, not plus, minus log absolute x minus 2 plus c. Or maybe if I wanted to get fancy, I would combine these under a single log as log absolute x minus 3 over x minus 2, remembering that the difference of logs is the log of the quotient. So what's the strategy of partial fractions? It's if I see an integrand or an integral with an integrand that has a rational expression where I have a polynomial in the denominator, and that polynomial is kind of roughly speaking composite. If it's composed of as the product of two smaller degree polynomials, can I break that fraction into two partial fractions or possibly more partial fractions, each of which is easier to integrate? I have a bunch of busy work over here I needed to do. I have two integrals to solve instead of one, but the two integrals I have to solve, the calculus I have to do is much simpler. I've done some algebra on the front end. I've done a good bit of algebra on the front end to simplify things down so that the calculus step, going from here to here, is a lot easier. Could I have done a direct attack on this? Probably. Probably by maybe completing the square in the denominator, using a substitution, and actually it would maybe end up looking a little bit like this arctan business up here. But that's a lot of work. That's a lot of places to make an error. That's a lot of calculus steps, right? I was able to do a bunch of algebra steps and make the calculus easy. I'd probably prefer to go this direction. Okay, so what's the general strategy to decompose a rational expression, say n of x over d of x, numerator over denominator, where n and d are polynomials, into partial fractions? Well, first things first, if the degree of the numerator is bigger than degree of the denominator, if I have like a cubic over a quadratic, I can do polynomial long division to break out just the polynomial piece, which is trivial to integrate, right? 3x plus 1 plus some rational expression, well, you can integrate 3x plus 1, no problem. So we integrate, or we break into a polynomial piece plus a rational expression where the degree of the numerator is less than degree of the denominator. So from this point forward, let's presume that degree of the numerator is less than degree of the denominator. We factor the denominator into factors that are either linear or quadratic. These are prime factors. Linear, obviously, but there are also some quadratics we can't factor. Easiest example is something like x squared plus 1. That is prime. We can't factor it any further in the reals. Although something like x squared minus 1, we'd want to keep going to get down to linear factors, to get down to factors that are indeed prime in the reals. And then we decompose as combinations of the linear bits and the quadratic bits. Note that the linear bits really only have constants as their numerators, but the quadratic bits that are prime, so things like x squared plus 1, if something like that popped up in the denominator, it could actually have an entire linear as its numerator. Right? So if I had, say, an x squared plus 1 in the denominator, I'd have to have an ax plus b as the kind of placeholder for the numerator. Okay, so let's take a look at this problem. Let's try to integrate this rational expression. Oh, and then of course, once we break up into partial fractions, we figure out all of our um, coefficients using the two methods I discussed up here, and then we complete our integration. Okay. First thing I notice here is degree of the numerator is 3, denominator is 2. I should be able to divide out a polynomial bit from here, right? It's almost like if I had, 16/7, I could write this as, well, that's 2 plus 2/7. So I have a whole number bit and then a fractional bit, and I can proceed forward from there with the fractions. Similar idea here. We could do polynomial long division. We could also do kind of a bit of a shortcut. But I think I'm not going to do the shortcut method. But you can kind of just reverse engineer what the polynomial bit has to be that comes out, because you know that, for instance, the 2x is going to go into the x squared. So you can kind of do a quick polynomial long division, but we'll just take the standard approach. 2x cubed plus x squared minus 7x plus 7. One thing to remember about polynomial long division, if we were missing one of these, if I just didn't have an x squared here, I would actually still put it in here, but I would put 0x squared as a placeholder just to keep everything aligned properly. If you don't do that, you kind of risk getting things misaligned and kind of jumbled up. But we don't need to do that here. We have our third degree term and then all of the other terms below it. So it's just good to go. All right, x squared goes into 2x cubed. How many times? Well, that is a 2x. 2x times x squared is 2x cubed. 2x times x is a plus 2x squared. And 2x times negative 2 is a minus 4x. I want to subtract this off, so I'm going to switch all of these signs. And then add. These go away. X squared minus 2x squared is, maybe I won't write all of these in red. That looks a little disconcerting. X squared minus 2x squared is negative x squared. Negative 7x plus 4x is minus 3x. I bring down my 7 plus 7. X squared goes into negative x squared how many times? Minus 1. That's a minus x squared minus x and plus 2. Again, I want to subtract this off, so what I'll do is flip the signs and then add. These go away. Negative 3x plus 2x. 7 minus 2 is plus 5. And I'm now down to a linear. Quadratic doesn't go into a linear anymore. That's my remainder. So I have that r of x, this thing up here I started with, is 2x minus 1 is the polynomial bit, plus, let me write this as 5 minus 2x over my denominator, right? The quotient plus the remainder divided by the original divisor. Same way that normal, just numerical long division works. I'm looking to integrate r of x, so I need to integrate the polynomial bit plus the integral of the rational expression bit. Well, integral of 2x plus 1, or 2x minus 1, is trivial, right? That's just going to give me x squared minus x. So it's really this part that I need to work on now. So let me come over here. Let me look at this rational expression where my degree of the numerator is less than degree of the denominator. And let me continue on with my partial fractions method. I note that x squared plus x minus 2, this is going to factor in to x minus 1 times x plus 2. Again, each of these factors is just a linear. The most that could be on top is a constant. Again, if I had anything bigger than a constant on top, if I had another linear on top, I'd be able to break out a polynomial term, maybe a fully constant term, but I'm not able to do that over here, so I shouldn't be able to do that on the right-hand side. Let me multiply both sides by x minus 1 times x plus 2. On the left, I'm left with 5 minus 2x. On the right, for the a term, my x minus 1's divide out, and I'm left with a times x plus 2. And for the second term, I'm left with b times x plus 2 divides out, x minus 1 left over. And maybe here, just to show an example, I'll do the 2 by 2 system method. Normally, I would probably do the substitute in x equals 1, substitute in x equals -2, work that way, but I'll just do a 2 by 2 system to give a demonstration. So I see that 5 plus -2 times x equals a plus b times x plus 2a minus b. So I'm just cordoning off my variable term and then my constant term on the right-hand side. I see that my variable coefficients have to match up. A plus b equals -2. And my constant terms have to match up. 2a minus b equals 5. This is my 2 by 2 system. And I have various methods of solving this. I noticed that my b's align nicely, so maybe I'll just add the two together. I have 3a equals 5 minus 2 is 3. My b's go away. A has to be 1. And then maybe I just plug in up here. 1 plus b is -2. B is -3. So a is 1, b is -3. That 1 plus -3 equals -2. That checks out there. 2 times 1 is 2. Minus a -3 is plus 3 is 5. That satisfies the second as well. So I think I'm pretty confident in this answer. A equals 1, b is -3. So this integral then is going to be integral of 1 over x minus 1 minus 3 times 1 over x plus 2. I know I got everything kind of jumbled up here because I'm trying to do it all to where you can see it, but if you have a notebook page, you might, separate one big area to do your scratch work and then, keep things a little more organized, but I'm trying to keep different pieces on the screen at different times here. So, but now that I've got this algebra done, I'm going to come back to this intermediate step of integrating the rational expression, the leftover rational expression. This is going to be log absolute x minus 1 minus 3 log absolute x plus 2. And let's throw the plus c on here now just to be safe. Or log absolute x minus 1 over x plus 2 cubed, I suppose, if we want to do that. Just bumping that 3 up into the power inside the log. And then remember that this actually comes back over here. And at the end of the day, the integral of my original rational expression, this whole thing up here that I started with, a lifetime ago now, I need to integrate my polynomial bit. That's x squared minus x. And then I need to add my remaining integral of this rational expression I did by partial fractions. Log absolute x minus 1 over x plus 2 cubed plus c. Right. And again, whether you put it in this form or whether you leave the logs split out like this, I think that's kind of splitting hairs as to what's simpler. Just a little easier for me to write the second way. Any questions on this one? Okay. I think we'll hunt these next two because I don't think I can. I was thinking, can I get halfway through one of them? But I don't even think I can get halfway through one of these and comfortably in the remaining 8 minutes. I'm going to end up just absolutely trying to race through them or something. So I'm going to punt these two either to a supplement or to next time. And we'll end the recording now. Let me turn that off.